Hi everyone and welcome back to my Thursday. Today we're going to do a chemistry Regents review on electron transfer, specifically oxidation and reduction. Firstly, oxidation and reduction are two things that are necessary for something called a redox reaction. Now, there is also something called half reaction or a half redox reaction, which involves either oxidation or reduction. Now, oxidation involves the loss of electrons, and reduction involves the gain of electrons. So a way that you can remember this is through oil rig. Oil oxidation involves loss of electrons, reduction involves gain of electrons. And whenever an atom gets oxidized, it's gonna become more positive. It's gonna become a cation because it's getting rid of that negativity. But when an atom gains electrons, it's going to become more negative because it's obtaining the negative charge of that electron. Now, whenever this happens, an atom obtains something called an oxidation number, and we can find this oxidation number in our periodic table of elements, and we look at the group number. So for example, if we take a look at oxygen is in group 16, or that column 16, and that means that it has 6 valence electrons. But in order to achieve a full octet, which is 8 valence electrons, it's going to need 2 electrons. So its oxidation number or its charge is going to be -2. Now, another thing that we need to know is voltaic versus electrolytic cells. Both of these undergo oxidation and or reduction. Now, there are a few differences. So in a voltaic cell, you typically have 2 cells or solutions. You have one salt bridge that carries ions in order to transfer ions and balance the charges, and it is spontaneous, so that means that it happens without a direct power source, and electrons are transferred from the most to least reactive metal, or the anode to the cathode. And lastly, it converts chemical to electrical energy. Now, an electrolytic cell, what it does is that it normally has one cell or solution. It uses an outside power source, which can be something like a battery, to power a non-spontaneous redox reaction. So non-spontaneous means that it happens unnaturally, so it's being controlled by something, and it converts electrical to chemical energy, and it still transfers electrons from the anode to the cathode. So now let's actually get into the problems. Most modern smartphones rely on rechargeable lithium-ion batteries to operate. The battery consists of an anode, where lithium atoms are embedded into a carbon matrix, and a cathode, like cobalt dioxide. When the phone is in use, the battery discharges, allowing an electrical current to power the device. The chemical equations below represent the half reactions and the overall cell reaction that takes place during the discharge of this battery. So let's do a quick annotation. So in a half reaction, you're going to either have reduction or oxidation happen. So let's first look at the half reaction number 1. We see that we have this E minus, which is another symbol for electrons, in our reactant side. But in half reaction 2, we see that the electrons is now in the product side. So if the electrons is in the product side, that means that it's being released, it's being produced. So it also means that we're losing electrons. So in this case, lithium, Li, is losing electrons. We also can tell because we see that Li is going from, we have our invisible 0 there, to then an Li plus. And we can assume that's Li plus 1 because also we only have one singular electron being lost. So again, if we're losing an electron, we're getting rid of that negativity and we're becoming more positive. So we can see that 0 to plus 1, we're adding 1. So we're gaining positivity. Therefore, we lost negativity. Now, in half reaction 1, we can see that the electron is in the reactants. So we're gaining electrons. So in this case, COO2 or cobalt dioxide is gain electrons. So now let's look at the problem. Using the provided information in figure 1, identify which specific component or particle in half reaction 1 indicates that a gain of electrons is taking place. So that's the first part. It's asking us to identify which component in half reaction 1. Now the second part says determine the oxidation states of all components in LiCoO2. So let's do part 1 on this side. So in half reaction 1, we see that an electron is being added to the reactants. Since it's being added to the reactants, that means that we're gaining electrons. Let's do number 2. So we need to find the oxidation states of all the components in LiCoO2. So let's let's split up this compound. We're going to have Li, CO, and O2. To figure out the oxidation numbers, we have to look at the table of elements. Since Li is in group 1, that means that Li is going to have an oxidation number of +1. And if we look at oxygen, as we spoke about earlier, is in group 16. And since it's in group 16, it's going to need to gain 2 electrons, so its oxidation number is going to be 2-. However, since we have 2 oxygen atoms, we're going to have to multiply that by 2, and we're going to get -4. Now, since this is a compound, all neutral compounds are equal to 0. So we need to figure out what the oxidation state of CO is. So we have 1 plus x minus 4 equals 0. Well, 1 minus 4 gives us -3, then -3 plus x equals 0. So what do I add to -3 to give me 0? That's going to be a +3. So x is going to be +3. So if I were to restate this, the oxidation state of Li is +1, the oxidation state of CO is +3, and O2 is -4. Now let's do the next problem. Using the equations in figure 1, illustrate the mechanism of electron transfer during battery discharge. Your response must explicitly identify the species that undergoes oxidation and the species that undergoes reduction. How the overall chemical reaction demonstrates the law of conservation of charge. So let's do part A first. So oxidation, again, we're losing electrons. And we can see that in half reaction 2, where we see the electrons in the product side. So Li is oxidizing because there's electrons in the products, and Li is going from Li to the 0 to Li plus 1. Then, now since Li is the one oxidizing, CO is the one reducing. The reason being is because it's gaining electrons. Now, in terms of charge, we can see this if we look at the actual equation. So in the overall cell reaction, let's figure out the net charges of each one. So since Li is by itself, it's considered a free uncombined element. So it's going to have an oxidation number of 0. Now since CO and O2, that's a compound, it's going to have to add up to 0. So we know that O2, oxygen, has an oxidation number of -2 times the 2 that we have here is going to give us -4. So since that's a -4, and this whole thing has to be neutral, CO is going to be 4 in this case, in order for the whole compound to equal 0. Now on this side, we have an entire compound altogether, including lithium. So this whole thing is also going to be equal to 0. But if you look at it carefully, it's the same rules apply. Oxygen, there's 2 oxygen atoms times the oxidation number, which is -2, that's -4. Now, since this whole thing has to add up to 0, we also know that lithium is in group 1. Since lithium is in group 1, it's going to be +1. So then 1 plus x plus -4 is going to equal 0. So let me just rewrite that. 1 plus x minus 4 equals 0. Again, 1 minus 4 is -3. So then plus a -3 is going to give us 0. So in this case, Li was 1, CO was 3, and O2 was -4. Taking that into consideration, we see that in both reactants and product side, the relative charge stayed 0. But before that, actually, let me just write down how we saw CO go from equaling 4 here to then equaling 3 on this side. So it went from CO4 to then CO plus 3, showing how then it gained an electron because it lost its positivity. So now we can write that the overall cell reaction conserves charge because the relative charge stay the same on both sides. So it stayed 0. So now let's look at the next problem. Based on the chemical equations provided in figure 2, identify the specific component or particle whose movement from anode half reaction to cathode half reaction establishes a transfer of charge. So in this question, it's talking about transfer of charge. And the way that we get a charge to change is whether we add or take away an electron. So our answer is going to be C, because we also see that in the anode half reaction, we're producing or we're losing electrons, and then the cathode half reaction, we're gaining electrons. Because again, whenever we lose or gain electrons, we're creating ions, and those ions have their own charge. Describe how the half reaction in figure 2 provides chemical evidence that the splitting of water involves a transfer of electrons. It's talking about specifically the splitting of water. And that's represented in the anode half reaction where we see H2O being split up, right? It's being broken down and it's releasing 4 electrons. So the anode half reaction is showing how the water molecules is releasing 4 electrons as products. But then in the cathode half reaction, we can see that 4 electrons are being gained in the reactant side. Question 5. Identify the chemical species that is being reduced in the system modeled in figure 2. Well, reduction, that means that we're gaining electrons. And if we're gaining electrons, it's going to be on the reactant side, which we can see in the cathode half reaction. And in this case, 4H plus is gain the 4 electrons. So the answer is going to be H plus. Question 6. A clean energy advocate claims that this electrolyzer system functions by converting electrical energy into stored chemical potential energy. Support this argument by describing the role of the external electrical power source in forcing the electron transfer. Well, we know that if we're converting electrical into chemical energy, that's an electrolytic cell. And electrolytic cells rely on a non-spontaneous power source. So we can say that the external power source is supplying electrical energy in order to force a non-spontaneous reaction, which in turn it's forcing the electrons away from the anode and onto the cathode, which is allowing the non-spontaneous redox reaction to occur where the anode is losing the electrons and the cathode is gaining the electrons. This way it's storing the electrical energy as chemical potential energy. Lastly, question 7. A field engineer changes the operating conditions of the electrolyzer by replacing the pure water feed with an industrial waste stream containing chloride impurities. A half reaction occurs at the anode, modeled by the equation below. So we already know that at the anode, we're losing electrons or we're oxidizing. And that's clearly represented in this equation because we see that electrons are in the product side. So now the question is asking us to identify the chemical species that undergoes oxidation and to provide evidence. So in this case, 2Cl or Cl minus is undergoing oxidation because in the product side we can see that there is electrons being released. To answer B, we're using evidence from the half reaction. 2E minus is being produced / released in the product side. We can also tell that this is oxidation because at first in the reactant side, Cl minus was negative, it had a negative charge, but then after in the product side, it was no longer negative. So it obviously lost an electron, it lost that negativity.